السلام عليكم ورحمة الله وبركاته طلابي وطالباتي الأعزاء طلاب الفيزيكال كيمستري لاب 1 كيم 355 I am Mahmoud Abdel-Latif and inshallah I will be your instructor for this physical chemistry lab which is given under College of Science Chemistry Department United Arab Emirates University. The first experiment in the physical chemistry lab 1 is the determination of the ideality of solutions. And we can determine the ideality of solution using different properties. And the property for today will be the viscosity. And as you see from the title, just to determine the ideality of solutions. We have two types of solutions, ideal solutions and non-ideal solutions. And the difference between them, it will be clear in the next slides. For the ideal one, first of all, solution is a mixture of more than one component, and we end up with a clear solution, one layer, so to say. For the ideal one, if you mix substance A, so to say, with this one, it will be rearranged in a certain way. For example, you will find the volume will be additive and the change of the volume will be 0. Let's see. For the ideal solution have molecules that do not interact with each other. There is no any association, no dissociation. Also, an ideal solution is a solution that follows Raoult's law under all standard temperature and concentration. The delta V of mixing of the ideal one is 0, and the enthalpy change of mixing also will be 0, which means that the volume is additive. And the enthalpy change is 0 because the intermolecular forces between the components of solution will be the same as the intermolecular forces between the pure substances. Okay, so there is no any change of the energy, so the enthalpy change will be 0. Only solution with low concentration of solid behaves ideally. For example, we are going to study in this experiment in two parts, ideal solution and the non-ideal solution. For ideal one, like benzene, toluene, chloropenzene, and bromobenzene. For the non-ideal one, it could be methanol with water, for example. For the non-ideal one, okay, if you mix together, the enthalpy change and the volume change will not be 0. So, because the intermolecular forces between the components of the substances will not be the same like the pure one. So this is the pure one, and this is the mixed one. So there is change. If you would like to get the change in the interaction energy, it won't be 0. It will be some values. It could be negative or positive, and it gives you two types of solution with a positive deviation and the negative deviations. And it will be cleared in the next slides. Okay, the change of the interaction energy, if it's larger than 0, molecules prefer to associate with each other instead of foreign species. If the U delta U is less than 0, it means the molecule prefers to mix with each other instead of their own kind. For the non-ideal one, as I have already told you a few seconds ago, the volume change of mixing will not be 0, and enthalpy change of mixing won't be 0 too. The non-ideal one, it's a solution in which solid and solvent molecules interact with each other or with one another with the different forces than forces between the pure substances. For example, like methanol and water, they form a non-ideal solution. The amount of heat is evolved is larger, and thus a change in volume is also seen. This is a summary behavior of various type of solution. If it's these, the interactive forces between solid and solvent, if they are the same, okay, the interaction forces between the pure substances will be the same like different substances. So the enthalpy change will be zero, the volume change will be zero. So the delta T of solution formation is zero. So there's no any deviation from Raoult's law. So it's an ideal solution, like benzene toluene. For non-ideal one, the interaction energy or the force, interactive force between the two components of between the solid and the solvent will not be the same like the pure one. If the interaction, so both this one and this one are non-ideal one. If the interaction between the solvent and solid is larger than the pure one, so it's difficult to the solution to evaporate, so to say. So you end up with negative deviation. And this one is exothermic. So the liberated energy is higher than the energy required to separate the pure one. So it's negative deviation from Raoult's law, and this one is exothermic reaction. The other one, the interaction forces between solid and solvent is less than that between the pure one. So it's easy for the solution to evaporate, so it will be positive deviation from the Raoult's law. And this energy, the liberated energy, is lower than the energy required to separate the pure molecules in the pure substances. So it's an endothermic reaction. So for the positive deviation, solid-solvent interaction or attraction is smaller than solvent-solute attraction. For the negative one, the solvent-solute attraction is larger than solute attraction. Okay, so let us go to the first experiment. We are going to determine the viscosity of different solution and see if these solutions behave the ideal or not. Okay, suppose you have a solution which is composed of molecular layers, as you have seen, okay, molecular layers. And if you apply, for example, a shearing force or driving force for the above layer, it will move, for example, in a certain direction with a certain speed. Okay. Actually, there is a friction force between this layer and the other layers. This friction depends on some parameters, for example, the velocity of the moving layer, the distance between this layer and the other layers, the surface area of that layer. Okay, these are molecular layers. This is a moving one, and this other layers. Okay, let's see. Actually, the friction force before that, okay, we can define viscosity of the liquid is a measure of that frictional resistance. In other words, or other definition, the viscosity is the resistance of the liquid to flow. So this frictional force is directly proportional to the surface area of the moving layer, okay, and also is directly proportional to the velocity of that layer, and inversely proportional to the distance between this layer and the other layer. If you have two moving layers, so to say, there is a difference between the velocity dv and distance between both is dx. So we can change this proportionality constant with equality sign, and we have to use a constant. In that case, we call it eta, which is a specific viscosity of a certain liquid, and it's characteristic for each solvent. Also, it's called viscosity coefficient. So we can calculate viscosity coefficient from this equation. Just rearrange that equation to end up with that one. Okay, it's called viscosity coefficient, or a specific viscosity of a solvent, and it's characteristic for each solvent. We can determine the viscosity of a solution using Poiseuille's equation, or Poiseuille's law, which is given in the front of you, in which eta equals pi b r to the power 4 t divided by 8 LV, where pi is the constant, v is the volume of the liquid flowing through the capillary tube, t is the flow time for that volume to flow, and b is the pressure head, r is the radius of the tube, and L is the length of that tube. As you see, there are many parameters here. It's not so easy to determine all this characteristic of the capillary or capillary parameters, the volume and liquid and radius. So later on, we are going to, instead of determine the absolute viscosity, we are going to determine the relative one. In CGS system, and CGS system means centimeter gram second, which is not SI unit. So in this unit system, the eta is expressed in gram, centimeter minus 1, second minus 1. And this unit is called poise, according to Poiseuille. In practice, smaller unit centipoise can be used, which is 10 to the power minus 2 from this unit. Okay, the SI unit, it should be in kilogram meter minus 1 second minus 1. It's very easy, just we can convert between this one to this one. So here we should divide or multiply by 10 to the power minus 3. And also this one we should multiply by the 10 to the power minus 2 from this one to this one, and second will be the same. So you end up with that. Okay, the SI unit is this one, so 1 poise will equal 0.0 of the SI unit. 1 poise, which is 1 gram centimeter minus 1 second minus 1, it will be 0.1 in SI unit, which is kilogram meter minus 1 second minus 1. Okay, another property which is very important to study which is useful to apply to fluid mobility is the fluidity. So another property for a solution or a solvent to study is the fluidity, and it's given by F, which is simply the inverse of the viscosity coefficient, the reciprocal of eta. So F, fluidity equals 1 over eta. So if we can determine eta, it's very simple to determine F. Okay. From the title of the equation, we are going to study the ideality of solutions. So we are going to measure the viscosity for solutions, okay, between two components. For a binary solution of a liquid which is composed of A and B, each pure liquid having fluidity Fa and Fb. If they are ideal, I told you that before, the volume is additive. In the same way, the fluidity is additive. So the fluidity of a mixture containing a mole fraction Xa and Xb may be approximated as the total fluidity equal the mole fraction of substance A times its fluidity plus the mole fraction of the other component times its fluidity. If they behave ideally, you can apply this equation. If the solutions are not behaving ideally, so this equation it's not valid, cannot be applied, cannot be applied. Okay. More specifically, for the non-ideal one, non-ideal solution, might be you have association or dissociation could happen for the formed solution. So you cannot apply that one. Okay? If you mix, for example, a complex with another substance, might be dissociation of this complex happen after mixing. Or if you mix two liquids, it can associate together, so you cannot apply this one. Okay, another parameter in which the viscosity depends on the temperature. And in general speaking, the viscosity of a liquid is decreased by increasing temperature. By increasing temperature, okay, so over a reasonably wide temperature range, the viscosity of pure liquid increases exponentially with the inverse of the absolute temperature. It's increased with the inverse. It means it decreases with increasing temperature. The relationship which studied the relationship between the viscosity and temperature, it's Arrhenius equation, which is given by this one. Eta equals A exponential E eta divided by RT, where A is Arrhenius constant and E eta the activation energy of a viscous liquid to flow, R is the ideal gas constant, and the T is the absolute temperature. And if you plot a relationship between the viscosity and temperature, you end up with this one. Okay, the viscosity decreases with increasing temperature, as you see. Okay. And if you take the logarithm, natural logarithm for both sides, so you end up with ln eta equal ln A plus E eta over RT. So plot a relationship between ln viscosity against 1 over T. It should be a straight line with the slope E eta over A. So if you plot ln viscosity against 1 over T, you end up with a straight line with the intercept ln A and slope E eta over R. Okay, so you can determine that. That's good. Let us go to the experimental part. In this experimental part, we are going to use Ostwald Viscometer to study or to measure the flow time of different solutions. And Ostwald Viscometer, it looks like this one, okay? Something like, okay, let's say U tube, and this is large side and this is smaller side. Okay, it's very simple. Just we're going to put, for example, 10 milliliter from this side. It will be there, so to say, and we're going to pull this volume to be above this fiducial line, and let this, this volume to flow down between this fiducial or these two marks, these two lines. So the experimental consists of measuring just the flow time required for a given volume of liquid to flow through viscometer capillary, this one, between the upper and the lower fiducial marks of the viscometer. Returning back to Poiseuille's equation, which is given by this one, so you have the radius of the capillary tube and the volume of the capillary tube or volume of the solution, and h the height, so to say, or the length of the capillary. So there are many, okay, it's not so easy to measure this kind of characteristic of the capillary. So we can use, as I have already told you previously, we can determine the not absolute viscosity by the relative one. And P is the pressure, by the way. We can replace this pressure by rho GH, and if you substitute it in that one, you can end up with this equation. Okay, so we can use the characteristic of the capillary or capillary parameters, the radius and volume, and okay, volume and radius and so on in one constant. The physical characteristic of a viscometer can be replaced by this constant, which equal to this one. Okay, so after substituting with the pressure with this one, you end up with this equation: eta equal k rho t, where t is the flow time and the k is constant, which is all this characteristic parameter of the capillary. Okay, so if you can measure the time t for a liquid having density r, you can determine the viscosity or relative viscosity of some solution. I told you that, okay, it's not easy to determine the absolute viscosity, but you can determine the relative one with respect to a reference solution. And the reference solvent here, we are going to use water. So to say, if you have the reference one, which is subscript with R, K is constant, the characteristic of the capillary, and rho the density of water, T the time flow of water. For the solution, we are going to determine, okay, it have different velocity, different density and different time flow. Okay, it's constant because we are going to use the same Ostwald Viscometer. I'm sorry for that. If you just divide this equation by this one, K will be cancelled together, and you end up with this one. The relative viscosity of a certain solution equal the viscosity of the reference one divided by the reference parameter, as you see, times the rho of the density of solution and T time flow of the solution. So divide this equation, you end up with this one, where eta r, rho r, T r are the viscosity, density, and the flow time for the reference liquid, and usually it will be water. So the objective for our experiment just to measure and analyze the viscosities of different solutions, ideal solution, which is toluene, paraxylene, and non-ideal solution, which is methanol, water, binary solution, and their components. We are going to use viscometer, Ostwald Viscometer, and 50 milliliter beakers, just 10 milli pipettes, and also pipette filler, viscometer, stopwatch, methanol, and paraxylene, toluene, and acetone. The part one, we are going to use it for non-ideal solution, and the part two, we are going to measure viscosity for ideal solution. Sorry for that. Using Ostwald Viscometer, just fix. I'm going to show that video for this experiment. Just fix a viscometer on its holder. Through the large tube, fill the viscometer with 10 milliliter of water. Use the pipette filler to pull them on the other side. And draw the liquid up above the upper fiducial mark. Allow the water to run back down and start the stopwatch once the meniscus passes the upper fiducial mark. Then stop the stopwatch as the meniscus passes in the lower mark. Just record the time. Repeat the above steps twice until the flow time agree within about 0.2 seconds. Okay, just empty the viscometer in a certain waste bottle. Okay, in order to clean it, we are going to use acetone, which is easily evaporize, and then drain or dry this acetone carefully using compressed air outlet under the fume hood. Okay, we are going to prepare different solutions, water and methanol that are 20% and 40%, 60%, 80%, 100% by volume of methanol. So in the first run, just we use 100% of water. The second one, just increase 20% of methanol, 8 milliliter plus 2 milliliter, then 6 milliliter, 4 milliliter of methanol. Okay, and so on until you reach 100% of methanol, and all these volumes or all this percentage by volume. Okay, keep in mind that just 10 milliliter of each solution is enough to do that. And you have to stir the solution before put it in the Ostwald Viscometer. We're going to determine the flow time of solutions. Okay, just dispose solution in certain waste bottles. Okay, and we follow the same procedure for all solutions we have. Just to collect our data in the following table. Okay, instead of measuring the density of each solution, it's given the density. This is the for pure water, which is the reference one. And this is the percentage of methanol, just by volume. I'm sorry. Okay, just we're going to do each experiment 3 times and take the average time. And these are the density, and use the previous equation to determine the eta, the relative for solutions. And here it will be the same, it's water. And we can determine the experimental fluidity, which 1 over this one, 1 over the eta. It's easy to calculate the mole fraction for water and the methanol, and you can calculate the theoretical fluidity using the previous equation. This is part 2. We are going to follow the same procedure, but instead of water and methanol, we use toluene and the paraxylene solution. The table or the results, we should do it here, and keep in mind that here we use water as the reference one. Water is used as the reference. In data analysis, we're going to use this equation. This is for the reference, eta water, raw water, time flow for water. Okay, we know the densities of solutions we have, and just we determine the flow time. Once you get this one, you can determine the eta, viscosity. Once you get the viscosity, just get its inverse to get the fluidity. Okay, the experimental one. The theoretical calculation, we use this equation. You should calculate the mole fraction of A and B, and you have the pure fluidity of liquid A and liquid B, so you can calculate the theoretical fluidity of solution and see if it behaves ideal or not. Okay, this is the validity of equation by plotting the experimental one versus XA and theoretical fluidity versus XA, also for both systems or for both parts, and just to comment on ideality of the two solutions. Actually, this, okay, see here in the viscometer, and here it's the holder or the, okay, just hold it in the stand, okay, and this is a pipette filler. Just we're going to see what we're going, okay? Okay, never use, withdraw with the mouse, use the pipette filler, so to say, as you see. A certain volume of the first component of the first solution, and just put it in this beaker. Okay, this is methanol, so to say. 10 milliliter, for example, and this is water. This is water. Another pipette, you should use it. And okay, pull or withdraw 8 milliliter of water, 8 milliliters of water, and mix them with the another component, which is methanol. See, okay, and you should stir carefully to mix the component of solution you have. I will show you. Okay, see, just mixing, stirring, and just put this 10 milliliter in the large side of the capillary carefully. See, okay, and it will collect it in that bulb, as you see. Okay, good. And then withdraw this volume of solution in the other side using the pipette filler or the rubber bulb. So, okay, the surface of the level of the solution increase in this side. Okay, till I would say it's enough. So I'm going to record the time or the flow time between the two fiducial marks. I'm going to show you. This is the first one. Once the meniscus come at that fiducial, just start the stopwatch and keep stopwatch working till the meniscus end up or reach to this fiducial line. Okay, see, I'm showing you the fiducial mark. So stop it. It's 17 point. Just record the time so you can determine the viscosity, the eta, and then the fluidity, and then you can calculate the theoretical one and plot it against the mole fraction. Okay, this is the first experiment. I hope everything is clear for all of you, and thanks. Thank you so much. And inshallah, in the next meeting, we are going to discuss together the hydroscopic determination of the molecular weight using the colligative properties. Okay? Until we meet again, wish you all the best and bye-bye.